Yeah, so you might have wondered that you saw this slide on one of the last podcasts, not last week, but the week before last week. And there was no remaining podcast to catch up here. And actually, I don't know what happened. So this is kind of the lost file. Maybe some conspiracy behind, I don't know. But anyway, now I'm happy to redo this podcast, the last podcast for 2 weeks before. So it catches up here after Kernel PCA. And here, this slide that you already have seen, but it was not explained to you, is just that to show you that matrix factorization, which is actually what you do in SVD and PCA and stuff like that. So matrix decompositions can be formalized as optimization tasks, which is a nice to have, because then you can just run standard optimization solvers to solve that problem, which is always a little easier than coming up with a different or your own algorithm in that case. Yeah, and here is how you can do that. Just that you know, I mean, as I said before, typically SVD and PCA are pre-implemented in most of the libraries, Python, whatever. But anyway, just that you know that most of those methods typically do it through the way of formalizing the whole thing as an optimization task. So recall that we have this decomposition of the data matrix in these three matrices here. In the case of SVDs, and the same, of course, in case of PCA. And you can rewrite the whole thing, as you see here, by two matrices actually. So a decomposition not into three matrices, but instead in two matrices, U and V transposed. U is actually the dot product, the matrix product of O with S. And this one here is S times A transposed, which is the V transposed. Yeah, and now you can formalize, as I told you before, the decomposition like SVD or PCA as the problem to solve or to optimize this Frobenius norm here, the Frobenius norm here of a matrix, or the squared Frobenius norm of a matrix here, of an n times m matrix. You see here, you just sum up all the cells of the matrix to the square, to the power of 2. Yeah, so the squared values of the values within the matrix, and that is the squared Frobenius norm, and you apply that to d minus this decomposition. Yeah, and of course it should be minimized in order to solve the whole problem. And you have the side constraint that these v's here, the entries in the v's, are orthogonal to each other, and also the u's here need to be orthogonal to each other. So there is an equals 0 missing. So just the side constraint is that both the v's and also the u's are pairwise orthogonal to each other, perpendicular to each other. So the scalar product should be 0 in that case, pairwise scalar product. Yeah, and that's it actually. And what is also missing with the missing podcast is that we had some further measures which we want to tell you about. It's just another snapshot of methods existing for feature reduction. And the first one are the so-called Fisher phases. And the Fisher phases is a method which is now not unsupervised but supervised, because you need training examples. Yeah, so and you use these training examples in order to generate new features where the discriminative power between the classes is increased, maximized, or whatever. Yeah, and for that purpose, you try to, how to increase the discriminative power of your target space, of your feature space. Well, you want to find a feature space where the similarity between objects from different classes is minimized. Yeah, or in other words, the distance between objects from distance classes from different classes is maximized. Yeah, so this is the between class scatter matrix you look at, which is called sigma b, and for that you use the covariance matrix of the class centroids. Yeah, so you just take the class centroids for each class 1 centroid and then compute the covariance matrix on these centroids. Yeah, so you take the centroids as a new data matrix. If you have k classes, you just have k centroids, so k objects, and you compute the covariance matrix of these k centroids. This is the sigma b here. And actually, the spread here should be large, right? So you want to find axes where the spread here is large. So the sigma b, the covariances are larger. Yeah. And then on the other hand, you want to maximize similarity between objects from the same class. Yeah, or in other words, minimize the distance within the class, between objects within the class. Yeah. And for that purpose, you use the average covariance matrix of all classes, which is denoted as sigma w. Yeah. So sigma b is the covariance matrix of the class centroids, and then for each class, say we have k classes, you compute the covariance matrix of all the k classes, and then take the average of those covariance matrices as the sigma w. Yeah? And obviously, along those axes, you want to have a small spread, so you want to minimize the impact on the directions from sigma w. Yeah, and how can you relate those two things now? Okay, you're looking for new bases. You're looking for new axes, the features, which are the b's here. So you determine new basis vectors bi, and you want to maximize actually this relationship here, because, well, we said we want to have a large direction or a large impact of those directions that emphasize the different classes, and we want to have a low spread along those directions where as long as we are within the classes. Yeah, so this should be large, this should be small. So overall, you want to maximize this term, and of course, again, by a side constraint. And the side constraint is easy because, of course, the features, the basis vectors, should be orthogonal, perpendicular to each other. So that's why you have this side constraint down here. Yeah. So once again, you look for the directions so that between the classes the spread is high, and within the classes the spread is low. Yeah, and that maximizes the whole thing here. And that's the idea basically of Fisher phases. And of course, it only works with the training set, so in a supervised setting. Yeah, that's it. Short remark on that. So there's just a very interesting, or by design, an interesting relationship to Fisher's discriminant analysis, which you probably know from KDD1 as one of the linear classifiers. So the vector having the largest eigenvalue corresponds to the normal vector of the separating hyperplane of Fisher discriminant analysis. So yeah, that's as I said, by design. Yeah. Fisher phases are limited to something, and the something is the assumption of monomodule classes. So each class is assumed to follow one multivariate Gaussian because we model them with one covariance matrix and then take the average. Yeah. So if your classes or one of the classes does not follow one Gaussian distribution, then the covariance matrix will have a very negative impact on the average covariance matrix of all classes. Yeah. So the assumption is that all the classes, and it's in here in this this sigma w, that all the classes for themselves can be modeled by a multivariate Gaussian distribution. You know? So multimodal or non-Gaussian distributions are not modeled well here, obviously, because, yeah, as I said, we take the idea of Gaussian distributions, and that's it. Yeah? And there are a lot of variants trying to get rid of those assumptions. So here are some names for it: relevant component analysis, large margin nearest neighbor, and stuff like that. So they are all based on the same idea, but do it a little different. So just that you know how to somehow classify those things here. Yeah, so here is a summary, and we can conclude finally this section on feature reduction and metric learning. So we have seen, or we got to know, some linear basis transformations like SVD, PCA, and stuff like that. So they are really mature to optimize feature spaces, especially the unsupervised methods. They of course rely again on specific assumptions, like in that case PCA and SVD. They delete the low variant dimensions, so they look for those dimensions or those directions that have a high spread, a large variance, and so the basic assumption is that those directions, those new features, provide more information for finding the patterns. If you don't have linear patterns, then Kernel PCA allows also to compute nonlinear kernel spaces, or PCA in nonlinear kernel spaces, which is appears to be a little weird, but all those kernels appear to be a little weird, but are mathematically extremely sound and extremely handy, actually. Yeah? The only downside, of course, is that you have to pick the right kernel for your data. Basic assumption, we already talked about that: direction of highest variance. Really have the most relevant information according to your pattern you're searching for. And we also got to know some supervised methods, at least Fisher phases, which try to minimize the within-class distances, maximizing between-class distances simultaneously, and finding the right features, or deriving new features that find a trade-off between minimizing and maximizing those two things here. And that's it. And hope you enjoyed the whole week, and stay tuned for the next chapters.